All right, let's dive in. Today, we're talking about electrostatics. And I know, that might sound like a heavy physics topic, but stick with me, because this is an invisible force that is literally shaping our world in ways you probably never even thought about. So, have you ever wondered about this? You're at a party, you rub a balloon on your hair, and suddenly it just sticks to the wall or makes all your hair stand straight up. What in the world is going on there? Well, the answer is electrostatics. Yeah, that's the word for it, electrostatics. And the most important part of that word is static. It means still. So we're not talking about the electricity flowing through the walls to charge your phone. Nope. This is all about charges that build up on something and just hang out, waiting for something to happen. Okay, so let's pull back the curtain on this invisible world, right? We're going to uncover the shocking truth, and yeah, sometimes I mean that literally, behind all these little everyday mysteries. And trust me, this is not some boring concept from a physics textbook. You felt this. It's that little zap you get from a doorknob on a really dry day. It's that crackling sound when you pull a sweater over your head in the dark. Or, when you shuffle your feet on the carpet just to go and shock your friend. That's it. That's electrostatics in action. So we all know what this feels like, right? The zap, the crackle, the cling. But how does it actually work? What are the rules? Well, it turns out there's a super simple, really elegant rule book that explains everything. And really, it all just boils down to this. Rule number 1, opposites attract. Positive and negative charges, they want to be together. Rule number 2, like charges repel. You put 2 positives together or 2 negatives, they're going to push each other away. And the third and final rule, this whole push and pull force gets weaker the further apart the charges get. That's it. That's the entire game right there. Now, this might sound a little familiar. Kind of like gravity, right? I mean, both forces work over a distance, and both get weaker the farther away you are. But here is the massive difference. Gravity only pulls. It only attracts. Electrostatics, it can do both. It attracts and it repels. And that two-way street is what makes it so powerful. Okay, so if these charges aren't even touching, how do they know to push or pull on each other? How does that force travel across empty space? Well, to get that, we have to imagine something we can't actually see, a field of force. See, every single charge out there creates this invisible bubble of influence around itself. We call it an electric field. Think of it like a charge's own personal space. And if another charge wanders into that space, it's going to feel a push or a pull. That's how they interact without ever having to touch. And that gravity comparison, it works perfectly here too. I mean, we're not physically touching the center of the Earth, but its gravitational field is still pulling us down. It reaches all the way out to hold the moon in orbit. Electric fields work the exact same way. They're just for charge instead of for mass. So to help us see these invisible fields, physicists came up with the idea of drawing lines of force. Just imagine them like little arrows. They always point away from positive charges, and they point towards negative charges. Simple enough. And where you see the lines all bunched up close together, that's where the force is super strong. Where they're spread far apart, the force is weaker. Oh, and one last thing. These lines can never ever cross. Makes sense, right? The force at any single spot can only point in one direction. All right, so we've got charges, which create forces, which travel through these invisible fields. But there's one more piece to the puzzle, energy. Think about it like a boulder sitting at the top of a hill. It has potential energy just because of where it is, right? Well, a charge in an electric field is the exact same thing. This concept is called electric potential. It's basically the amount of stored up energy a charge has just because of its location. It has nothing to do with whether it's moving or not. It's all about its position, its spot in that field. So let's go back to that hill idea. Imagine the electric field is like a landscape full of hills and valleys. Now, if you have a positive charge and you try to push it closer to another positive charge, that's like pushing a boulder uphill. It takes a ton of effort and you're storing energy in that boulder. But the second you let go, it's going to roll right back downhill, releasing all that energy. That electric hill you're pushing against, that's basically what voltage is. So, invisible rules, electric hills. Why should you care? Because once we understood all this stuff, we could use it to build some absolutely incredible technology. This is the payoff. This is where this invisible force becomes a seriously powerful tool. Okay, ever use a photocopier or a laser printer? That whole thing is basically an electrostatics machine. A laser draws your document onto a drum using static electricity, an invisible image made of charge. Then it rolls that drum through a bunch of ink powder or toner that has the opposite charge. And what happens? The ink sticks only to the parts the laser drew. It's a perfect opposites attract in action. Or how about this one? Painting a car. The way they do it now is brilliant. They give the car's metal frame one type of electric charge, and then they give the paint droplets coming out of the sprayer the opposite charge. So what does the paint do? It literally wraps itself around the metal, clinging to every nook and cranny. You get a perfect, even coat with almost zero waste. And it's not just for factories either. Think about farming. They can now give pesticide spray an electric charge. Why? Because it makes the little droplets cling way better to the plant leaves. You get more protection for the crops and less of that chemical just washing off into the ground. It's a smarter way to farm, and it's all thanks to these simple rules of static. But before we finish up, I want to leave you with just how mind-bendingly powerful this force actually is. It is unbelievably strong. So strong that if you could somehow take one standard unit of charge, 1 coulomb, and put it a meter away from its opposite, the force pulling them together would be 9 billion newtons. That's like the weight of a giant aircraft carrier. It's immense. The only reason that spark from the doorknob doesn't blow a hole in the wall is that we're dealing with just the tiniest fraction of that potential power. So, there you have it. From something as simple as a balloon sticking to your hair, all the way to the high-tech robots that build our cars, these simple rules are everywhere. They are the invisible architect of so much of our world. And that just leaves one big, exciting question. Now that we know the rules, what are we going to build with them next?